This is problem 8-54M. A round shaft, 40 millimeters in diameter, carries the load shown in the figure, which is on the next page. Compute the maximum shearing stress in the shaft, part A. Compute the maximum stress due to bending in part B, and then specify a suitable steel for the shaft to produce a design factor of 4 based on yield strength in either shear or bending. Now what we've got is a beam, and the beam has a round cross section. Okay. Now there are simple supports at the ends. There's a distributed load of let me put it in here, 1 kilonewton per meter, and that occurs over 0.24 meters of length. Then there is a distributed load of 2 kilonewtons per meter for 0.6 meters. There's another distributed load of 1 kilonewton per meter on the other side for another 0.24 meters. But there's also 2 point loads, each at 450 newtons. And they're where the distributed loads change. So we're supposed to essentially come up with shear and moment diagrams first, and then calculate the shear and the bending stresses, and then specify steel. So let's see. Let's start off with the reactions. That would be first. So if we call this point A and this point B, if we sum moments about A, we should get 0. And how would we do that? Well, 1 kilonewton per meter times 0.24 meters would be 0.24 kilonewtons of force. Does that make sense? This first distributed load will have an effect of 0.24 kilonewtons. Where will that act? I'm calculating moments. Where will the resultant of the first distributed load act? In the center, right? At 0.12 meters, right? So the moment arm is 0.12 meters, okay, for that first distributed load. Continuing along, we've got the next distributed load, which is 2 kilonewtons per meter times 0.6 meters. So what's the resultant force for that 2 kilonewton per meter distributed load? 1.2 kilonewtons, right? You guys just tired of this, or are you not sure? How many people are not sure? Okay, so most of you are just tired of it. Okay, that's fair. Fair enough. Where is this going to act? Well, let's see. It'll act at the center here, so 0.3 plus 0.24 is 0.54 meters. Okay. And then what else? Well, we've also got these 2 point loads. Let me deal with them last. So then finally here, we're going to have the same 0.24 kilonewton load acting at 0.24 plus 0.26 plus half of 0.24. So let's see, that'd be 0.36, so this is 0.96 meters if I did it right. Does that make sense?
No, it's all been 0.66.
Well, we've got 0.24
Oh wait, 0.6.
plus half.
Yeah.
Okay, so 0.9. No, you're fine. I appreciate you guys checking it. Then we have the point loads, 450 newtons. Now I'm going to write that as 0.45 kilonewtons to make my life a little easier. So let's see, 0.45 kilonewtons multiplied by the moment arm, 0.24 meters. And then finally, let's see, 0.45 kilonewtons multiplied by a moment arm of 0.84 meters, so 0.24 plus 0.6. Okay, now all of this has to be balanced by the reaction over here. Fortunately, since this is symmetrical, the load over here will be exactly the same. So once we're done with this, we've got our reactions. So then, let's see, since I've got all these positive, apparently I've taken that direction as positive. So minus the overall length, which is .48, so, sorry, I'm thinking of putting the load first, 1.08, thank you. Is that right, 1.08? Yeah, that's right, 1.8 meters. So now we can calculate B. To calculate B, all we have to do is take this whole mess here, which I'm going to ask you guys to do, plug it in, and then divide by 1.08 meters. Okay, so you're going to have kilonewton meters over meters, so this will just be kilonewtons of force. Yes?
Since it's symmetrical, couldn't you just say some forces in the y equals 2 times the reaction?
Yeah, we could. Didn't think of that. That would be easier. So why don't half of you do it one way, half of you do it the other? See what we come up with.
1.53.
1.53. Did you use the moment method or the sum of forces method?
The moment method.
Okay, so somebody with the force method and somebody with the moment method, please verify that. Good point. I didn't think of it. Good idea. I'm not sure if I agree with that. I've done the math right here.
Yeah, I'm getting 1.29.
That's some.
1.29?
1.29.
Yeah, by the sum of force method or moment?
Sum of force.
Okay, yeah, I've got 1 point, well, half of that, 2.58. Anyone with the sum of moments come up with 1.29? Okay. Yeah, I think 1.29 is the correct answer, not 1.53. And that's just based on adding all of these loads and then dividing by 2, which makes more sense. Okay? All right, now that we've got the reactions, now we can actually begin the interesting part of the problem. The shear diagram in kilonewtons would look like what? Well, let's see, we've got 1.29 kilonewtons, so we go down to 1.29 and the negative side, okay? And as we go along, we're going to increase, well, let's see, we've got more acting, so we're going to increase this line. Let's see, at a rate of 1 kilonewton per meter. So if we move over 0.24, then we'll have to increase by 0.24 kilonewtons. So let's see, let me match that up. So at 0.24 kilonewtons, this would end up being, well, let's see, let's put it over here because this is going to get messy otherwise. 1.05, right?
Isn't that upside down? Shouldn't it be the other way?
Let's see.
Increasing.
I mean, if you're.
Shear is going to be down, so
If you keep
shear
it
is
consistent,
actually
it
positive down.
doesn't make a difference.
So yeah, you're right. We should be consistent with what we've done before. So yeah, you're right. Actually, it would be the other way. Keep me honest, guys. I need it.
I mean, as long as you stay consistent to the whole problem, it really doesn't make that much.
That's true. That's true. But I want to observe the sign convention. So this would be 1.0. No, 4. No, 5. That's right. Okay. So then we have to drop down by another 0.45. Right. So that would take us down to what? 0.45, 0.6, isn't it? So this point is 0.6. And then we're going to keep decreasing, but now we're going to decrease at a faster rate. We expect the shear to cross in the center here, right? Because it's all symmetrical. And let's see, that's about the best I can do there. Okay, so let's make sure that that works. 0.6, well, so 0.3 times 2 would be 0.6, so sure enough, we do go to 0. That makes sense. And it's going to be symmetrical, so there's no need in worrying about the rest of it. So go down to negative 1.05, and then back up to 0. So that should be okay, where this point would be negative 1.29. Now we need the moment diagram in kilonewton meters. And I'll need a little bit of help here. Make sure that I get all of this right. All right, so the area of this section here can be calculated pretty easily. Take 1.29 plus 1.05 and divide by 2. After you do that, multiply it by 0.24 meters. Okay? So 1.29 plus 1.04 divide by 2 times 0.24. How much moment do you get? Got to start at 0 moment. It's going to go up something like this. Try that. So what's the magnitude of the moment here?
.2808.
0.2808, that sounds reasonable. Anyone second that? Okay, good. What next? Well, notice this concentrated load does not cause a concentrated moment, right? It's just a concentrated load. So all we need to do is add more area, right? So this area here would be 0.6 multiplied by 0.3 over 2, right? Because 0.3 is going to be half that distance. So 0.3 times 0.6 divided by 2 because it's a triangle.
0.09.
0.09, thank you. So that 0.09 has to add to this, right? So we've got to come up to a point here where we have 0.09 plus this, which is what? 09, that would be 3706? No, 9, so 7. Thank you. 3708. Now, it's just going to be symmetrical, so why bother with the rest of it, right? We're interested in the maximum shear, which occurs here, and the maximum moment, which occurs there. The whole point of doing this was to say that the maximum moment is 0.3708 kilonewton meters, and the maximum shear is 1.29 kilonewtons. Okay? That was the whole point. Because now what we want to do is calculate the maximum bending stress, which would be my over I. Well, we'll plug in C, so we get the maximum. And now we need to concern ourselves with the cross-sectional properties. Now it's a round shaft, it's 40 millimeters in diameter. So how far is the neutral axis from the top of the beam? 20 millimeters, right? So 0.02 meters, okay? Now how about I? How will we get I? Well, we'll have to go to the back of the book and look up I for a circular cross-section. It's pretty easy. It should be pi d cubed over 64 if I remember right. Let's see, so area properties. Let's see. I'm looking at the wrong thing. Yeah, so d to the 4, pi d 4 to the 4 over 64. So let's calculate I. So pi times 0.04 meters to the 4th over 64. Let's not be 64. Plug that in your calculator, please, and give me a number.
1.26 times 10 to the negative 7.
And that would be meters to the 4th. So I just plugged it in right there. Okay. So now we should get kilonewtons per meter squared. What is a kilonewton per meter squared? Not pascals. A kilonewton would be kilopascals, because a newton per meter squared is a pascal, so this would be kilopascals. So plug all this in your calculator, and let's see how many kilopascals of stress we have. Okay.
Getting 59,014.65.
59,000 point what? No, 59,000 how much?
59,014.65.
Oh, 14, okay, so 04, 014. So let me just write this as megapascals. Because if it was 59,000, I moved the decimal place over 3. Now we've got another factor of 1,000, so kilo times kilo is mega, right? So there's the stress, the bending stress. While we're at it, before we go and look up a material, let's calculate the shear. Now the shear is pretty simple. Why? Because this is a circular cross-section. What's the equation for the maximum stress in a circular cross-section?
4V over 3A.
Good. 4V over 3A. Well, that's not too bad because we already know V is 1.29 kilonewtons. The area is just the area of a circle, right? So we need pi times 0.04 squared over 2. Is it 2 or 4? I'm not thinking. Here, let's make it easy. There. So let's take pi r squared. Make sure it works. And of course, this has units of meters. So we'll again end up with kilopascals because we've got kilonewtons per meter squared. Okay. So plug this in your calculator, please, and let's find out the stress. That's the shear stress in this. Notice we've chosen the maximum shear load. What we're doing here is choosing the maximum shear stress, which is at the center of the circular cross-section.
1,368.7.
1,000 how much?
368.7.
How about that in megapascals? One of the reasons I like problems like these is it shows you the difference in the stress. Usually, the stress due to the moment is much higher than the stress due to the, okay, so anyway, we're supposed to calculate, or we're supposed to determine a material with a design factor of 4 based on yielding. So basically what we need to do is multiply both of these numbers by 4. What do we get when we multiply these two by 4? 60, 60, 122, what, about 240? How much?
236.
236?
06.
Yeah, let's leave it there, megapascals. And this one times 4? 5 point something, right?
5.5.
5.5. Now let's go look for a material. Which one's limiting here? Obviously this one, right? So we need some material that has a yield strength of at least 236 megapascals, and I think they said steel. So we'll just go to steel, page 714. Page 714. Now we have to be a little bit careful here. Even though this is small, we have to be careful because we can compare this directly to the yield strength. The yield strength is a normal type of thing. Does that make sense? The shear is not. In fact, for the shear, what we have to do is take the yield strength and divide it by 2 to get the strength in shear. Does that make sense? Or if they have a yield strength in shear, we could just use that, but they don't. In effect, what that means is in order to compare this, this must be less than a yield strength over 2. In order to compare this, we should go ahead and multiply this by 2, right? So we need some material with a yield strength greater than, well, this times 2 is 11 megapascals. So you have to be careful about that. It's still not enough to make it the more important thing, okay? But it's important to know that. So what material would work? Any of them. Right? Most of them would work just fine. I don't think there's any on here that wouldn't work. Okay. Any questions? Comments? All right, that's it.